Good afternoon and welcome to Algorithms and Data Structures today. Last week, we continued with trees and we briefly looked into balanced search trees and saw that we need to balance search trees. If we don't, they may look like a list and then we are unable to search or in them or amend or manipulate them efficiently. And for the details, I asked you to look into the book or watch this video to get a bit of an understanding because contrary to most other algorithms and data structures courses, I wanted to spend the remaining time of trees on something that is probably something you need to study in greater detail since most of you study AI. And we looked into decision trees. So we've been using decision trees as a user for a long time, actually. And for a decision problem, we now want a decision tree and finding the optimal decision tree. So the smallest one is a computationally very challenging problem. In fact, it's an NP-complete problem. So we are unable to find in time the optimal tree for a large amount of examples. However, with a heuristic, we can find an approximate solution very efficiently. And for this, we study the ID3 decision tree learning algorithm, which is a concrete application of trees. And we studied this algorithm, looked at an example, and saw how we can also determine the information gain and calculated an example and got this tree. And there's another data set for which I got this tree here. And this was also in the coursework, in particular, problems 12.5 and 12.6. 12.6 is the mandatory problem. And today there were quite a few students in the lab, despite today being a day between the public holiday yesterday and the weekend. And I saw already one student who has implemented decision tree learning entirely with his group, and another group has completed most of it, I think. So that's great. And we just have a few weeks left. So if you have any problems with the coursework, do come to the lab sessions. And concerning the schedule for the next few weeks, so next week, Friday, the 6th of June, is a lecture-free day at our university. So not my decision, but set by the university leadership. And the same applies for in 3 weeks. So June the 20th, it's also a lecture-free day. Has to do with all these public holidays. It's something I don't like because it makes the scheduling of my classes more difficult. So we don't meet next week and in 3 weeks. But we meet in 2 weeks, and in 2 weeks we have lab sessions from 8 to 1 on campus, and then as of 2 p.m. we need to do an online double lecture that will be recorded, simply because we don't have class at all next week and in 3 weeks, and we still need to progress with the content of this course. Then we also started looking into maps and hash tables. And we implemented, so we first looked at what is a map. It maps a unique key to some value. And we saw how we can implement a map. And for this, we implemented the unsorted table map, which is some very initial kind of dictionary. So we map from a key to a value. But it's not very efficient yet, as we saw. And what we want to do next is we want to have hash tables which work as the native dictionaries in Python work. And one question is now, one student wants to know how the hash table works. We're in the process of this, so I'll do the revision now of what we did last week, and then we continue with the hash table because we've just built the initial data structure. So what we built was fairly easy, was the unsorted table map, which is internally a list, and we can add new key value pairs. For key value pairs, we have the map base class, and in there we have an inner class, which is the item class. And for an item, we have a key and a value, and we can compare keys. So we can compare item objects with the equal, not equal, and less than, so we can bring in some order, and we do these comparisons on the key. And what we started doing is we've looked into the map base, which just contains this inner class for items. We've then implemented the unsorted table map, which I will revise next. And we have implemented the hash map base, which is a base for hash maps. But there are different ways how we can handle so-called collisions. And today we will implement the chain hash map. And all of this is tied to the Python collections module, the immutable mapping class, which comes with some basic features. But map base is abstract as well as the hash map base because we still need to further implement concrete features. And there's one question here about other types of maps. I'll mention them at the end of this chapter. So we're starting now with the hash tables, and the ones asked by a student in the chat or something we'll look at probably the very last slide of this chapter, concretely so-called tree maps and sorted table maps. But they don't matter for now. And the unsorted table map, what it does is it's a table and I can add key value pairs, so objects of the item class. With get, I can read out the value for a key. With set item, I can add a key value pair, or I replace a key value pair with a new one for a key that exists already. And I'm also able to delete a key value pair and get the length as well as an iterator. This is what we studied last week in detail, and we saw there are some limitations, and that's why we want to do hashing, so that we don't actually store the, so if we had a regular lookup table like this, we would require that the key is an index, but we also want different keys, not just integers, maybe a string or some other kind of object. And we actually want to scatter them more smartly throughout this table. And we don't want to have a lot of empty blocks in here. So what we want to do is hashing. So we hash the key, and hashing means we're turning the information in the key into some index in the lookup table. And what this could be is something we saw here, that we have key value pairs. So for example, 1D, the 1 is the key and D is the value. And we would put that here, for example, into a so-called bucket at index 1. And the same with index 3 contains a bucket with like 3F, but also other key value pairs like 14Z and 25C. So we're able to store multiple key value pairs in a bucket. The only question is, how can we implement these buckets exactly? And that's something we will face today. We also saw different ways of hashing keys, and we've implemented the hash map base, which is a basis for, or a base class for multiple possible hash tables. What we implemented was we are storing the actual table or the array that we saw here. So this is the one we are storing, and it has a certain capacity. Initially capacity 11, what we said. We count the number of elements, plus we have a little bit more details for the hashing, but I said how the hashing works exactly doesn't matter too much. I said a few details last week when we implemented it, but what we want to do is we want to be able to hash a key. And now we can get items, we can set items, and we delete them. And each time when we have a key, we first hash the key. And what we get is an index j in that list. And then we want to set or get the item from a bucket. So we still need to implement bucket get item for the index j and the corresponding key, because there could be multiple items at that bucket. And the same for setting and deleting. We made it up to here last week, and we discussed a problem, which is, or a challenge. It's the collisions. Collisions means that two distinct keys have eventually the same position or the same bucket where we would put them in. And when we look at the visualization from before, these are collisions. We have different key value pairs that are in the same bucket. And now the question is, how do we implement these buckets? And that's exactly what we need to do now. We need to handle collisions. And for that, the literature typically describes two different approaches that are most common: separate chaining and linear probing. We will focus on separate chaining, and I'll explain it here. This is a visualization of what separate chaining would do. So we have our list or array, whatever, say list, with different indexes. So we have 13 elements, indexes 0 to 12. And what we see visualized here is we only visualize now the keys of our items, not the corresponding values, because they're just tied to the key. But in order to keep this visualization simple, we will just look at the keys. And we see there are different keys that we tried to add, like a key that is 54, and through the hashing here would be in fact a very simple function. It would take the key value and say modulo 13, and 54 modulo 13 is 2, so we would put it here. Then maybe next the 18, and 18 modulo 13 is 5, so we put it at the corresponding index. And we do the same maybe with 10, and 10 modulo 13 is obviously 10. And we do this also for the 25. But now, for example, we want to add also a key value pair for which the key is 36. And 36 modulo 13 is 10. But we have already put a key value pair at that position. But we need to put now another one, another key value pair for which 36 is the key. And with separate chaining, what we are doing here is the way we implement this bucket is a list. So we put a list at that index 10 and put the first key value pair. If there is another key value pair, we put it there as well. And the same has happened with 38, 12, and 90. So they were added step by step into that list that started with 25. What we see here is with putting these lists, so the separate chaining, in fact, our hash function here is a very poor one, because what we actually want is we want to spread out the elements as much as possible among our 13 index values. But we sort of have clusters here. So this very simple hash function is maybe easy to calculate, easy to visualize, but it's not a very helpful one. And one student asked if we can imagine this as an unsorted table map. And that's correct. We've implemented the unsorted table map last week, and now we're going to use it in our next class in order to represent these lists where we put key value pairs. We will discuss complexity later, but what we still want initially as a node for complexity is we want to spread out with a good hash function our items as much as possible here. And if we have filled a certain number or a certain proportion of these indexes, we actually want to resize. And resizing means creating a new list that is bigger, maybe for example a double size, and then redistributing all the items we had put there already with the goal of also spreading them out as much as possible. What we don't want are super long lists, because if we have super long lists, yes, we get quickly to that index, but then we need to linearly walk through the unsorted table map. And that's very slow, especially if these lists are large. So our goal is to spread them out as much as possible, have these lists or these unsorted table maps as short as possible. And if we keep adding too many elements or more than a certain threshold, we want to resize this one and redistribute all the elements in a larger hash table. And that's exactly what I will implement now for you. And for this, I will share my screen. We had implemented last week different classes. I will just quickly copy paste them here because we've already implemented them, so there's no need to implement them again. What we did last week was the map base. We've implemented the unsorted table map, and you don't need to start this from scratch, but you have the resources zip file in our Nextcloud directory, so you can just copy paste from there. And we also needed the random module in order to build our own hash function, and we've implemented the hash map base. So I've copied now all that we had implemented last week, and we will now implement our chain hash map, which is a concrete implementation of the hash map base, which is still abstract. And what we need to implement now are strategies for getting an item from a bucket, setting an item in a bucket, and deleting an item from a bucket. Plus, we need to think about the iterator. So, because the get item in the hash map base simply says we're using a bucket get item. Now, when our chain hash map inherits from hash map base, it inherits the get item. So this one we simply inherit, but then when we call it, we need a concrete implementation for the bucket get item. So later, when we call get item or set item of an object of chain hash map, it will call this one that we inherit and execute our concrete implementation, bucket get item, set item, as well as delete item. So this will be bucket get item with the corresponding signature, that we have an index J, which is the bucket, as well as the original key with which we need to keep working. So what I need is a reference to our bucket. And what I need is the table, which is one of the attributes that we had created in HashMap base last week. So I need a reference to the corresponding bucket, which is index J, which the hash function has determined for us. And now I need to check a few things. I could very easily just return the bucket and the item k or index k with it. Because remember, when we implemented the unsorted table map, we also implemented a get item method for the unsorted table map. And the bucket, later we will assume, is just an object of the unsorted table map. So with index k, we get the value from the unsorted table map object to which this bucket reference refers to. But later we will see in the bucket set item how to create this, and it could happen that initially there is simply nothing at bucket. That bucket just refers to a non-reference. And if that is the case, then we need to raise a key error. Because there is, because if I don't check this and I call bucket index k, this will also lead to an exception, but one that comes simply because of the programming error, because this is a non-reference. So I rather check if it's a non-reference, and then I return or raise a proper exception that would match this problem here well. This was the simplest one, but we assume now that we have these unsorted table map objects here. So let's see how we can actually put them there. So we need the bucket set item. When you look at set item from the hash map base class, we see we pass the index J of the bucket and the key value pair. So as two separate parameters, K and V. And what I need to check now is if that bucket is actually none. Because what I want to add now is a key value pair. And if the bucket is initially none, I first need to create an unsorted table map object and put it there. So I'm creating an object of unsorted table map, and I put it at index J in my table, which is that list of references to objects of the unsorted table map. If this condition does not hold true, we already have an object there, so we don't need to recreate. And what we need to do now is we can say I'm looking at my table at index j, which is the unsorted table map object. And I'm putting a key value pair there because we had also implemented set item for the unsorted table map class. And I could say I'm increasing the size by 1 because I have added now an object. Do you think what I've just implemented always works or does not always work? If you think it works, what I have just implemented, send me a green reaction. If you see some shortcomings, maybe send a red sticker, turn on your mic, and tell me in the chat what you think could be improved. So green sticker, if you think the implementation is fine to add a key value pair, or red sticker if you disagree. So one student wonders what happens if we have that key already. And that's correct. This is something that I need to look in now because I'm just putting a key value pair, but maybe that key exists already and I have now reached an invalid state because I have just put a key value pair to replace one, but in fact, I have increased n. So I need to do something about that. And one way how you can implement this is we could say the old size is the length of our bucket, so the unsorted table map. I am now putting the object there, the key value one, and then I could actually check if the length of our bucket has changed. And the length of our unsorted table map has changed if something was actually added, if I have not replaced a key value pair, but added a new key with its corresponding value. Then this condition holds true for the unsorted table map object. And then I can also increase the n of my chain hash map. So the student that responded this in the chat saw it correctly. What I also need to implement now is the bucket delete item, which was also called in the hashmap base delete item method. And this is actually very similar to what I'm doing in the get item. So first I'm getting a reference to my bucket. Then I'm checking if the bucket is none. If so, I raise a key error. And then we had implemented delete item for the unsorted table map class, which goes through and deletes the key value object from the unsorted table map. And I can invoke this by calling del on bucket at index k, because this will invoke then the delete item method of the unsorted table map that we implemented last week. And obviously, first I need to check if the bucket actually exists. And if not, I'm raising an error. The last thing I need to implement is the iterator strategy. And one way how we can implement this is we have already implemented the iterator for the buckets, so for the unsorted table map, and I can reuse this, but I need to go through here the buckets first. So I'm going through all my buckets in the table from left to right. If the bucket is not none, it actually exists. If there is nothing in the bucket, I can just skip it because there's nothing to iterate. And then I yield from the bucket because I cannot just call yield on it because I needed a generated delegation because in the bucket, which is an object of unsorted table map, I will get multiple items back step by step. So I need to yield from this. So we've discussed, I think, 2 lectures ago, the concept of generator delegation. And there was also some coursework problem on generator delegation, and some students discussed it today with me in the lab, which was very good. So this is actually the implementation of our chain hash map. Let's test it. So we can say hash table is, so we have a chain hash map object, and we can try to put in something. So for example, we put in a string as a key, and as the corresponding value, we put just, say, an integer. We can do the same for 2, something like this. We can now get the length of the hash table, which looks okay. We can try to get this now. So hash table and the index or the key we are passing is 2. So what we get is the corresponding integer. So you are most welcome to test this a little bit more as part of the coursework. And you will see that it actually works. However, there are a few. So I'm now skipping a detailed test of this. I mean, we can try also to delete an item, so hash table with key 2. The length of the hash table has now been reduced, and if I'm reading it, I obviously get my key error. So feel free to test this a little bit and debug it, and you will see that it actually works. When we go back to the implementation of the base class, the hash map base, we had one very interesting thing, and we had this set item in the hash map base, which we implemented last week, and we also thought about the resizing. So it's something we implemented last week already, which you remember, and we said we would resize if the number of elements we have in our hash table is greater than half the length of the table. So, which is greater than half of the capacity. Then I would resize by saying 2 times the length. So I'm doubling the capacity, and I'm subtracting 1. That's something that a book recommends. So we get to actually an odd number, which helps with the prime numbers and distributing the hash as well. The question is, why is this threshold useful? Where we say the number of elements, when it's greater than half of the capacity, why do we resize then? And this is something we will study in a few slides and come back to this. But the beauty of our implementation is that chain hash map, all we needed to do was implement concrete strategies for bucket get item, bucket set item, as well as the iterator. And so what we have just implemented is this one here. But I told you also from before, we have implemented this class now, chain hash map, with one concrete strategy how to handle the buckets. There are other strategies how you can handle the bucket. For example, with the probe hash map, that's a different approach, which we're not implementing, but I'll quickly mention the concept, because we've said separate chaining is one approach how we can handle collisions. That's the one we've just implemented, but there's another one called linear probing. And linear probing is visualized here. So we don't put unsorted table map lists at the individual entries, but rather what we do is we want to add a new element with a key 15. And the key 15, for example, would then be the index 4, where I would put that key value pair. But there is an element already, and what I'm doing then is I'm trying to go to the next index and put it there. I would put it at the next index if it's possible. If it's not possible, I would go to even the next index, and I would keep doing this until I find a free index where I'm putting that element. And that's called linear probing. Linear probing, here we see the hash functions again, very simple. We just take the key, which we suppose to be is an integer modulo 11, and we only visualize the keys, not the values. And then when you search an element, for example, you want to look up key 15, you would go to where the hash function puts you, to that index, and you would check at that index, is that actually the key that I'm looking for? If it is the key, I can just return the corresponding value. If it's not, I would check if there is an element to the right. And if there is an element to the right, I would just keep going. Because of linear probing, the element may have been put to the right. Here I'll check again, is that the key I'm looking for? If not, I just keep going until I find the element. And if I don't find the element, but an empty spot, then I would return or raise an exception, because that key cannot exist then if there is an empty element, because if the key existed, even because of linear probing, it would have been put there where we have this empty element. So linear probing is something you can also fairly easily implement. It's not part of the coursework because I think the separate chaining approach, so the one we implemented in ChainHashMap, is typically the more common one. But if you wish, you can quite easily implement linear probing on your own as well. Now, let's think about the complexity of our approach. This table applies to both approaches, separate chaining as well as linear probing, but we only implemented in detail the separate chaining, so the ChainHashMap. And let's think about the complexity. I think the one that is fairly easy is the length. From the length, we just read out how many elements we have stored in N. So in the worst case, this is O of 1. The iterator is obviously for the hash table O of N, because I need to read out all N elements. And that is exactly the same as when I compare it to a list. So if I just have an unsorted list in which I'm storing these elements, iterating over all of them is N, reading out the length of the list is 1. Now, the point where it gets more interesting is the get item, set item, and delete item. With get item, for a list, an unsorted list, finding that one element that I'm looking for or finding out it does not exist is O of N. Because in the worst case, I need to go through all the elements in the unsorted list. And with the hash table, we now distinguish between expected and worst case complexities. Because expected, look at this one here, expected would be that I calculate the hash, and then because this one here is stored in the RAM, I can access any index in the same amount of time. And imagine I'm looking for key 18. I would go to index 5 then, because of the hash function, look at the first element and return it, if that's the one I'm looking for. So this would be in constant time in O of 1, because all I need to calculate is the hash and then do a random access to this index. But this is only expected and assuming I spread out well. If I have poor hashing or just too many elements in here, what could happen is that I'm storing a lot of elements in some of these unsorted table maps. Imagine I'm looking for element 90. Index 12, yes. So this is constant time to get here. But here I may have a huge amount of examples, maybe a certain proportion of all of the elements, say 80% of all the elements. And I need to walk to the very last one. Then this is not constant time anymore, but actually worst case O of N. So the best thing I can do is have a good hashing technique to spread out as much as possible and keep these lists or these unsorted table map objects as small as possible. Sometimes, yes, I need to store a few elements, but it shouldn't be a big part of the amount of the overall elements, but only very short unsorted table maps. So the same applies to set item, where I need to put in an item. If there is nothing in the unsorted table map yet, that's easy. If there are a lot of elements, I need to add it as the last element in the unsorted table map. The same for deleting. If there's just one element in that unsorted table map, I can easily delete it. If I need to walk through a lot of these items and delete the last one, that's slow. So if I spread out well with the hashing and the hash table is not too full, then getting, setting, and deleting has an expected complexity of O of 1, but obviously a worst case of O of n, where I simply have an overfull hash table with maybe too many elements in it, or that the elements just don't spread out well and I have a few super long lists in here. So the question here is one student asked if the worst case can only happen if one bucket was full and the item we're looking for is the last item in it. Well, that would be one example. Obviously, if I try to add thousands of elements in here, then it would also be O of n, because then I would have a lot of buckets that are all super full. And that's what I need the resizing for, that I resize and spread out all these elements more in among these different indexes. So resizing is key. If I don't resize, this approach here will become super slow. So that's very important and something to bear in mind. So here are these complexities. For the list, obviously, unsorted getting, setting, deleting is all O of n. And here, for the hash table, if we do it well, it's O of 1 in the expected case, but obviously, worst case, O of n. So this makes hash tables very interesting, because these expected ones, are constant and do not depend on n in the expected case. In the worst case, obviously, they do. So what is important is good hash functions to spread out. We've built quite a complex one in the code, which works far better than this one here. And we also need to think about the resizing. And resizing for this, we had discussed that just before, when we looked again into the set item of our hash map base, and we said, if we have more elements than half the capacity, then we resize. And that's what I said up to here, including last year. And then one student wandered and read the Goodrich book and said he would like to learn a little bit more. And that's why I've added a few more slides. So if you ever see a topic that you feel should be covered with a few more slides, let me know and I will add it. I will try to still try to discuss it this year then. However, if it's for some past chapter, it would only be for the students next year. And one student here approached me last year at the end of the course and said, maybe we could have talked a bit more about the resizing. And so I've added this year a few slides. So this was in the HashMap base, what we have done, what I've just shown you. And what is the rationale behind this one? What we can calculate is a ratio lambda. And the ratio lambda is the so-called load factor. And what we calculate is the number of elements, small n, divided by the capacity, big N. So if we have, for example, 8 elements in a capacity of 10, then the load factor would be 0.8. And the literature says that that load factor of a hash table should be bounded by a small constant, preferably below 1. And as long as this lambda is O of 1, then these core operations on the hash table run in O of 1 expected time. So the literature recommends keep this load factor, so the proportion of elements in related to the capacity, this should be preferably below 1. With separate chaining, something we have implemented, something we can see as this load factor gets close to 1, the probability of collisions greatly increases, and this adds this overhead by going linearly through these unsorted table maps. And this will lead to linear time operations, especially heard a lot if these unsorted table maps are quite long, and then we are not in O of 1 constant expected time anymore. There are experiments carried out, and the book reports them, an average case analysis, and they suggest that when we do separate chaining, the load factor should always be should be less than 0.9. For linear probing, where we don't have these unsorted table maps, but rather go to the next element and so forth, the load factor, when it grows beyond 0.5 and starts getting closer to 1, then we see certain clusters of entries in the bucket, and they start to grow as well. So it gets problematic as of 0.5. And that's why we said when we have reached half the capacity, then we would actually resize. For the separate chaining, you can reach technically a load factor of more than 1. That's technically possible if you don't resize, because you just keep adding more and more elements. Say we have, say, 10 indexes and we have 100 elements spread in here. Then we have these long unsorted table maps. Then we have a load factor of 10, something we don't want, but it's technically possible if we don't resize. With the linear probing, the most we can achieve is a load factor of 1, because we always just keep going to the next element. We don't create these unsorted table maps. So technically, this one here cannot grow beyond a load factor of 1. But for now, we'll try to keep the load factor at 0.5 at the very most. This is what the literature recommends. And that's what I've added this year as an extended discussion, because until last year, I didn't discuss this in detail, and one student wished to learn a little bit more, and I'm happy to have mentioned this with a few words today. There are just a few more, or this is just some more text of what I have said already for your revision, how the resizing works. When we resize, we just increase the number of indexes in the hash table, and then each element gets redistributed by getting rehashed and get put at a proper location. And ideally, we break up these long unsorted table maps. But this is just in writing what I have said before. Now, 2 more things about hash tables. You know now how to build your own hash tables, which is great. In Python, you can create a dictionary either like this. You can say D is a dictionary, which is a hash table, or like this. It's just the same what you're creating here. So this is equivalent to this one. Now, what I actually would like to have is a nested dictionary. So a nested dictionary would be something like I have a key 1, and then in that dictionary, so key 1 is a key, and that one would return a new dictionary, and in that dictionary, I would have a key 2 and then store a value in there. If I try to create something like this up front, it leads to an error, because all I have in D right now is an empty dictionary, and I'm unable to create a key and directly create an empty dictionary and then another key in there. Has any of you ever worked with nested dictionaries in Python? If you have green sticker, if you have never worked with nested dictionaries in Python, red sticker. These nested dictionaries, so one person has, maybe you want to tell us either in the chat or orally what you have used nested dictionaries for, because the others have not done this. So so I'll wait for your answer either orally or here in the chat, and I just keep talking until then. So these nested dictionaries, they're actually quite helpful if you have multi-dimensional data that you want to store. And for example, also a tree could be represented as a nested dictionary. So if you
Yeah,
try to, yes, please go ahead.
basically just uh, using it to store any information where you need complicated data structures in another complicated data structure, right? Not
Mhm.
really for any algorithms, though.
Okay, just to store complex data structures, fine. Thank you very much. You could also represent a tree like this, that maybe the first level you would have these different branches of the tree, and then each subtree would be represented by another dictionary, which is a subtree. So if you think about the coursework, maybe decision tree learning and how to represent a tree, you can extend the class for trees we have implemented 2 weeks ago. However, you could also use a dictionary to represent a tree. Now, if I want to create such a nested dictionary, I'm unable to build it directly like this, but rather what I would need to do is I would need to go and say, I want a key one. So this is a string, and the value would be a new dictionary. So we can read out and see what's now at key one. It's a dictionary. And then my statement from before would work because I say I'm accessing key one, which is a dictionary, and in there I'm putting a new key value pair for which the key is key two and then value as the value. And I can try this. And now what I see in D is, in the total dictionary is I have a key one as a string, and as a value, I have a sub-dictionary, and in there I have a key and a value. So I have these nested dictionaries. This actually looks quite similar to JSON files in case you have ever worked with them. They could also be represented as such a structure. But the initial statement I had tried here in line 18 does not work. So what I need to do is I need to create an empty dictionary first for that key and then again. Now, this is quite boring, especially if I have highly dimensional data. I don't want to manually create all these empty dictionaries in between. But what Python offers is in the collections module, it actually offers a so-called default dictionary. And the default dictionary will create you default values when needed. You can either do a default dictionary on dictionaries or on other data structures. And now I have created D. So D is just an empty default dictionary. And if I take my statement from before on D and I want to add key one and have a nested dictionary in there, then the intermediate empty dictionaries are all created automatically for me with the default dict. So in case you ever want to build such nested dictionaries, don't build this manually, rather use the default dictionary. But default dictionary is very powerful. You can do far more with it than just what I have shown you here. There's something very interesting, and feel free to study this. One student asked me when we started today about other types of maps. It turns out there are many more maps than the ones we have looked at. There are so-called sorted maps, there are tree maps, and the whole types of data structures like how to build sets or multi-sets. So a multi-set is a set, but you can have duplicate values in it, but the order of your values does not matter. All of these are strongly related to the maps we have just built. And we don't have time in this course to discuss sorted maps or tree maps or sets and multi-sets. The book discusses them in detail in case you want to study them, but they're not further relevant to this course because we've now looked at the standard hash tables with the chained hash maps, and that's enough for now. But if you're curious how to build sorted maps or tree maps or sets and multi-sets, all of this actually quite related to what we have just done. So feel free to look into the book. Now we are at a very interesting point in this course. This is the point where a typical algorithms and data structures course would finish. Because what we have done is we have started to motivate the course. We have looked at graphs as a very generic data structure. We've built graph algorithms, and then we started looking into complexity of algorithms. And then we started building lists, which are just some type of graphs with constraints. And we saw all sorts of variations of lists. First, array lists, then queues, stacks, but also linked lists, a totally different approach. Then we studied recursion and did search, binary search, and recurrence relations that help us to understand the complexity of recursive algorithms. Sorting can be described well with recursion in many cases. And for trees, we also need recursion. And we saw how to sort data, so we can search in the data efficiently or bring it into some sorted order so we can manipulate it easily. Trees are a different approach to storing and manipulating data very efficiently because we've seen that trees bring in order and we can balance trees. And maps and hash tables are a totally different approach and they come with their own complexities. So this is where a typical course would end, but we still have 1 month for this course. And I think we want to be better than the other 90% of the courses like this. And that's why there are 2 things left. At the very end, in a few weeks, I will talk about quantum computing, which is a modern or newer approach to computing that is becoming more and more popular, but there's also a lot of hype and speculation around it. So this is something we'll do in the last lecture. But in between, we have time to discuss a few selected algorithms. What I see every year is this chapter keeps growing and more algorithms are mentioned here. Very importantly, we only discuss some of them and only the ones that we discuss are relevant to the exam. As you may have seen, I've created this new list on YouTube so I can share recordings of past discussions of some of those from the last few years with you. This year, we will look at fast matrix multiplication, we will look at prime number generation, and we will look at the Plume filter. In past years, we've also discussed the random number generation and the fast inverse square root. If you're curious, the recordings are cut and available in this other YouTube playlist, but only the algorithms discussed this year are relevant. Today, we are doing the fast matrix multiplication, and in 2 weeks, when we have this double lecture as of 2 p.m., we look at prime number generation and the Plume filter. String matching is something that is part of your coursework as part of the mandatory problem, and union find and median of medians is something I will just mention very briefly at the end of the chapter. So today we'll spend time on fast matrix multiplication. Next week, a double lecture on prime numbers and the Plume filter. And then the very last lecture in a few weeks about quantum computing. And then we have 1 more lecture for the revision and preparation for the exam. Here, I personally like this chapter because, all these foundations we have discussed are very important, but I personally also like some variation because I've been teaching this course now for 5 years and I have more than 30 years up to retirement. So I also need some change. And obviously, I need to make sure every year that each chapter is up to date, but with these foundations, there are not too many changes. So the selected topics chapter also helps me to prepare some new algorithms or some other content, and every year I personally have some variation. And we got a message here. There's a question if string matching is also relevant for the exam. Yes, because everything from the coursework is relevant for the exam. And you need to study string matching. But since string matching is already the focus of the mandatory problem, I would hardly put this as a focus into the exam. And actually, none of the past exams has ever discussed the string matching, but theoretically, it could happen in the exam as well. But if you do the mandatory problem, which you need to do in order to be able to sit the exam anyway, you should be very well prepared with that. Now let's look into matrix multiplication. Matrix multiplication is an algorithm that you learn in school, for example, at the end of high school or in your first or second semester. And matrix multiplication is used for a lot of different stuff. For example, for matrix inversion, for computing the determinant of a matrix, for solving linear systems, but there are also more concrete applications like training a neural network or predicting in a neural network. This is something that you can describe very, very well in terms of matrix multiplications, plus a few other things, obviously. So matrix multiplications are super important. Do you have any other examples that you want to share with us where matrix multiplication is important? I'll wait for you to send this to the chat. If you think you have any other examples where matrix multiplication is important, just send a green sticker so I see if anything is coming, or send a red sticker if you have no other examples where matrix multiplication is important. And there's a green sticker, so please turn on your mic or send this to the chat, and maybe some other students want to be sharing something like this as well. Meanwhile, I will already switch to the iPad. So one student here says matrix multiplication is important to gaming. Yes. So matrix multiplication is important for gaming and computer graphics. That's correct. Maybe for SVD, singular value decomposition. Yes, because you have this decomposition and you want to put all together again. You need matrix multiplications. Yes. So what is a matrix multiplication? So we want to multiply a matrix A times B and get a matrix C. What I personally like is a notation that is something like this, where I put matrix A here, matrix B there, and matrix C down here as the result. So what I have is, for example, a 2 times 2 matrix, 1, 3, well, let's say it's a 2 times 3 matrix, something like this. And I have here a matrix for which we can, just thinking about some examples, we say this is dimension M, this is P, so we need P elements here as well, and here M elements. So we can say we put here, say, a 1, a 2, and a 4. Here, a 1, and a 0, and a 2. So what we see is M is 2, P is 3, and M and, excuse me, this is not an M, this is obviously an N. So M is 2, P is 3, P is 3 there as well, and N here would be 2, for example. Now, who of you knows this kind of visualization to multiply two matrices? Because every year there are quite a lot of students who have not seen this kind of notation like this, to use this tabular format. If you have seen this before, let us know, because it really helps to multiply the elements now, because I want to calculate this element here. And what I need to do is I have this column vector and I have this row vector here, and I need to multiply, different color, need to multiply these elements piecewise together. So 1 times 1 is 1, 2 times 3 is 6, and 4 times 4 is 16. So I would sum these products together, which would then be 23 as the result. And similarly for, well, let's make them the same size. Similarly here, well, turn this into green, then we have this column and this row, and we also multiply them piece by piece. So the 0 times 1, 1 times 2, and 1 times 4. So 0 times 1 is 0, plus 1 times 2 is 2, plus 1 times 4 is 4. And the same is something I would be doing for the next elements. So I would have this column here and multiply it with these rows. So I personally like this visualization for matrix multiplication because I can see the corresponding rows and columns very well and match these and multiply these elements piece by piece and then sum the products together. So do you think this kind of visualization for matrix multiplication is helpful? Just let me know if green or red, if you find this helpful or not. Some do, some don't. So remember, this was A, this was B, and this was C because I had put these arrows down there. And now, what is the complexity of matrix multiplication? So I have one dimension, M, then I have P, and P must be the same so I have P here and P there. They must be the same. Otherwise, I'm unable to multiply these matrices together. And I have N. What do you think would be the complexity of matrix multiplication? Complexity. It's O of what? I'll see if you can guess this, what the complexity of matrix multiplication would be. And if you know it, send it to the chat. We have one guess in the chat. Maybe someone else wants to guess what the matrix multiplication could be. So one person here says O of n times m. Any guess still any other guesses what the complexity would be of matrix multiplication? Is it O of n times m? In fact, it's n times p times m. Because n, p, and m are variables of the sizes of these matrices. So it's O of n times p times m. Now assume that we just pick the largest one, or that they are all the same, or we just pick the largest one, then it would be O of n to the power of 3. This would be the complexity of matrix multiplication. And the question is now, because O of n to the power of 3 is quite slow, can we do this faster? Can we multiply matrices faster than to the power of 3? And it turns out we can. And this is something I will show you now, partially here on the whiteboard, partially on the slides. And we will see an algorithm called the Strawson algorithm, named after the mathematician Mr. Strawson, who published this, I think, in the late 60s. And he found a way how we can do the matrix multiplication faster than to n to the power of 3. What he said is, as before, C is the product of A and B. So we have matrices A and B, and we multiply them and we get a matrix C. And he also said, just a note, A, B, and C, they must be, so they are an element of R, which stands for the real numbers of 2 to the power of n times 2 to the power of n. So what it means is the number of rows and columns must be a multiple of 2. If your matrices are not of that size, you would just fill the remaining elements with zeros. And it's about real numbers, but that's what this notation means. A, B, and C have real numbers, and each of the dimensions is a multiple of 2. And if they are smaller, we just fill the remaining entries. Now, what we also say is, we just take the notation from before, where we have A, B, and C, and we actually now don't think about concrete elements in here, but block matrices. So what we are doing is a block matrix can also be visualized like this, if you wish. So we take each matrix and split it into 4 equally sized pieces. So A11, A12, A21, and A22. Same for B. So B11, B12, B21, and B22. And C11, C12, C21, and C22. One thing that I need to highlight is A, B, and C, as well as these partitions in the slides, they are always in bold. So C and A and B, as well as these block matrices, are in bold. It's something I cannot write very well on the iPad, so I don't make them here now explicitly in bold. But if you see them in the slides, what I always try to do in my math slides is, if I have, so just for you as a note on the notation, the notation I personally like, a small small character is a scalar, so a numeric value. A bold, try it again. So this would be a bold A, that would be a vector, and a bold capital, this would be a matrix. And maybe this A doesn't look very nice, more looks like a Q. So now it's bold. So a regular lowercase character is a scalar, a bold one is a vector, and an uppercase bold one is a matrix. So this is something that I personally use as a notation, but in the slides, this is easier to type than here. So all of them are now obviously to be imagined in bold. And if I use just the approach from before of how I multiply these elements, then obviously my C11, in order to calculate it, I would multiply A11 with B11 and A12 with B21. So it's A11 times B11 plus A12 times B21. And we can do the same now for C12. So for example, in green, that we take the A11 and multiply it with B12 and A12 with B22. So I can write this out. C12, which is this one here then, it's A11 times B12 plus A12 plus B22. Now, what I want from you is that you are continuing the scheme without looking into the slides for C21 and C22. And if you have them, please send them to the slides, not to the slides, to the chat of how we can calculate C21 and C22. If you have this, send it anytime soon, and then we can compare, and then we can see how we can actually speed it up. So anyone has the first one? If you have it, or at least on a piece of paper and haven't typed it yet, send maybe a green reaction. If you don't have it yet, maybe a red reaction. So we have a green reaction, then please tell us in the chat what the solution for C21 would be, how we can calculate it. I'll wait for you to send this, but it's obvious in some B's and A's. And if you have the first one, send it to the C21, send it. I haven't received it yet. So I got something in the private chat. So C21 would be A21 times, well, wrong color, A21 times B11 and A22 times B21. That's correct. So it's A21 times B11 and A22 times B21. So what you sent me in the chat was almost correct because you wrote in the chat B22, but it's 21 because it's this one here. And for C22, so this one here, we would calculate as A21 times B12 and A22 times B22. So I'll just write this out. It's A21 times B12 and A22 times B22. So these are block matrices. These are not scalar values yet. It's just our big matrices A and B and C are partitioned into 4 equally sized matrices. But what I see in here is in order to calculate my 4 C's, what I have is 8 multiplications. I have a multiplication here and there. I have a multiplication here and there, there. So 8 multiplications. Multiplications. And multiplications are expensive because they are O of n to the power of 3. We've seen before, multiplications are expensive. Now I want to include you for another quiz. If I add 2 matrices, A and B, so adding, what is the complexity of adding? O of what? And these matrices are now n times n matrices. What do you think the complexity of adding 2 matrices would be? If you have a guess, green sticker and send it to the chat. If you have no guess, red one, please. Got a right one here in the answer. So adding 2 matrices is O of n squared because I need to go through all the elements in A and B are n times n many elements. So n squared. So adding two matrices is far cheaper than multiplying two matrices. So what we see is here we have these additions of products, but what is expensive are these 8 multiplications. The additions are cheap. And now the big question is, can we do this in cheaper than 8 multiplications? Can we do this with less? Do you see a very trivial way how I could use less multiplications to create these 4 C's? If you see a very easy way, green reaction, if you don't see an easy way how we can get rid of 8 multiplications, send a red reaction. There's a red reaction, and I also don't see an easy way, I have to tell you. There's no easy way that is just obviously trivial how to do this. So what I'm screen sharing is now just what I had written down before, my A, B, and C, and how to calculate my C's from the A's and B's. And I hope there's no typo, but the ones in the slides are correct. So 8 multiplications. And then Mr. Strossen recognized in the 60s that you can in fact do this with 7 multiplications instead of 8. And now, what did he do? He created 7 auxiliary matrices. So M1 to M7. And each M1 to M7 contains 1 multiplication. So we have the multiplication here, we have one there, and so forth. Plus some additions or subtractions of our block matrices. But additions and subtractions are cheap. Multiplications are expensive. So Mr. Strossen calculated these 7 auxiliary matrices. And then he found a way, and it doesn't matter exactly how he derived this. This was probably long research for him to find M1 to M7. And then he found a way, but what's important is we just need 7 multiplications, more additions and subtractions. But then he found a way how these M's can be combined to get to our original C's. And finally, these are just additions or subtractions of the M's. So it turns out we can calculate the C11 to C22 by combining through additions and subtractions of these auxiliary matrices. And for the auxiliary matrices, we only need 7 multiplications. Now, these are block matrices. It's very important that we're not done yet. We need to continue this recursively. So these block matrices, we have these multiplications. But in order to do these multiplications, we cannot do them on the blocks, but rather we need to take each block matrix and recursively divide it into, again, block matrices. So we do this recursively until we only have single elements left, so real numbers. So we keep doing this until we have a block matrix that is then a 2 times 2 matrix. And in each block, we would have a single scalar value. Then we are done. So it's a recursive algorithm. But we keep doing this, and it turns out that with this Strossen algorithm, I can do it cheaper. And the Strossen algorithm has, in fact, a running time complexity of O of n to the logarithm of 2, O of n to the binary logarithm of 7. So this is the binary logarithm of 7, which is around 2.8074. So it turns out we can do the matrix multiplication faster now. Not as O of n to the power of 3, but O of n to the power of 2.8074 and so forth. And that's a major improvement. Are you impressed that we can do the matrix multiplication faster than O of n to the power of 3? If you feel this is amazing, let us know with some positive reaction. If you're not impressed, send us a different reaction. So this led actually to a major speed up, because if we have very large matrices, it makes a difference. And nowadays in machine learning, you have super large matrices with millions of elements or more, maybe billions of elements. Then such a speed up is definitely noticeable. But we're adding more lower order work, like more additions and subtractions. That's why typically the Strassen algorithm is only used when you have dimensions where n is greater than 100 or something like this, because we have more lower order work. And while from a complexity point of view, lower order work doesn't matter, in real running time, it does matter. So we actually don't apply the Strassen algorithm to super, super small matrices because we just add a lot of overhead, but we do it for very large matrices. And once we have n of 100 or something left, we just keep doing the naive matrix multiplication there. Otherwise, it just becomes slow. And that's why if you look at linear algebra libraries, what they often do is for matrix multiplication, yes, they implement the Strassen algorithm, but only run it when n is, for example, greater than 100 or some other threshold. So the Strassen algorithm is fantastic. It's a fantastic piece of mathematics. It comes with a little drawback that actually your numerical stability is reduced. Numerical stability here means it matters for if you have float values or real values. If you just have integers, no problem, no change. But as you know, in a computer, there are a lot of float values we cannot represent precisely, but we use the IEEE 754 format, which comes with a little bit of imprecision. And then if you add more operations, the result that you get would be slightly off than if you didn't do these extra operations. So the numerical stability is reduced compared to the naive algorithm. It's not a mathematical problem, but it's a problem how we represent numbers in a computer. So, and it turns out that the work that Strassen did led to a lot of further algorithms in the coming years. So we see Strassen did this in like 1969. And after that, lots of new algorithms were proposed, even with a better complexity. So up to here, less than O of n to the power of 2.4, so 3 something, 2.3 something. All of this was proposed after 69. So it was, and even Strassen here again proposed something. But it turns out that none of these algorithms ever really worked in practice. Because yes, they come with a better complexity, but none of them actually would work on real-world matrices faster. But it would only work on matrices that are too big to be stored by today's computers, because only for very large n they actually run faster because they have a lot of these extra lower order terms. So the Strassen algorithm was only the one that was really used in practice, and even only when like n was 100 or greater. And this is exactly where this course finished with matrix multiplication until a few years ago. And it looks like, well, these are all foundations of computer science. They don't change anymore. It turns out they do. In 2022, a very interesting paper was published by DeepMind. Who of you has heard about DeepMind, a subsidiary of Google? If you have heard about them, let us know with a reaction. So some have heard. DeepMind is this Google subsidiary that, for example, built AlphaGo, an AI that was able to beat the best human Go players some 10 years ago or something like this. And they actually did something very interesting. They used that AI they used to play Go and extended it. And they used it to find a new matrix multiplication algorithm. So a new, better matrix multiplication algorithm found by an AI. What they used was reinforcement learning. So this is one pillar of machine learning, which doesn't matter for today, plus a few other things like in a tree search and so forth. So the AI they used to play Go, they amended with some tricks and they applied it to the problem of matrix multiplication. And the AI was supposed to find a better matrix multiplication algorithm. And it actually worked out. So this was discovered in 2021 and the paper was published in 2022. So an AI that they called Alpha Tensor finds a faster matrix multiplication algorithm, one that actually works in practice on matrices we're using today. What it does is it discusses the Strassen algorithm from a slightly different perspective because what the Strassen algorithm we have looked at was at the end, it was 2 times 2 matrices, the smallest ones. What here was used was it was split in a different way. Like we would not multiply 2 times 2 matrices, but the blocks would actually be 4 by 4 matrices. But it's just a different type of the plot or different size of the blocks, not 2 times 2, but actually 4 times 4. And if you do this with the Strassen algorithm, what you would have, so if you apply the Strassen algorithm not to 2 times 2 matrices, but 4 times 4 block matrices, then you would have something like 49 multiplications. Why? Because we had these 7 multiplications for 2 times 2, and then if you square the 2 times 2, so it's 4 times 4, then it's 7 squared, 49 multiplications. Still better than the naive one, because the naive one would then have been 8 times 8, so 64 or something like this. And with Strassen, it was 7 times 7, 49. But it turned out that with the matrix multiplication algorithm found by Alpha Tensor, it was 47 multiplications instead of 49 on multiplying these 4 times 4 block matrices. And when you look at our Strassen algorithm from before, we had something like this here. We said the binary logarithm of 7, which was then 2.80 whatever, but this was about 2 times 2 matrices. You could say also the log 4 of 49, which is just the same value. So if you say down here, the log 4 of 49 is 2.8 whatever. So this was the Strassen algorithm on 4 times 4 block matrices, not 2 times 2. But what DeepMind found was a new matrix multiplication algorithm, which only needs 47 multiplications on 4 times 4 matrices. So the log 4 of 47 is 2.7773. So it's a better complexity, which is nothing new because better complexities were found here for many decades, but none of these new algorithms actually led to improvements for today's matrices because all these lower order terms just made it slower on today's matrices. But the one that DeepMind found runs faster in practice on matrices we have available today. There is more lower order work, but not too much. So in fact, it runs faster for matrices we're using today. Now comes one shocking thing. So for the 2 times 2 matrices, we wrote this out here very well. For the 4 times 4 matrices, writing it out would be a little bit more work, but could be done. But for the one that DeepMind found, they published this in their paper. And it was something like this. So we have these 4 times 4 matrices. And in order to calculate our C's, so C11 up to C44, this is shown here, and we need 47 auxiliary matrices. So here's H47, And for each auxiliary matrix, we have one multiplication. And no human could have found this. Strawson, what he published in the 60s, he found out by taking pains for a long time manually. But these ones here were not found by humans, but actually by an AI, and it was an extension of the AI that bet the best human Go players. So this is something I found super interesting when this paper appeared 3 years ago, and then I added it here to the course. If you want to read the whole paper and see how the AI works, check the paper in Nature. This is obviously how that AI works is not relevant to this course or the exam, yet what you should just know is that foundations of computer science, yes, they are not ultimately stable. AI is making a lot of changes now, and a lot of heuristics that people came up 50 or 60 years ago are being disrupted by AI. And now an AI found a better matrix multiplication algorithm that actually works in practice. This is something that I've now been talking about for the last 2 years in this course. We will discuss quantum computing in a few weeks. You could also use a quantum computer to actually do matrix multiplication. But for larger matrices, that is just theory so far, because the quantum computers we have available today, they're not really practical for large matrices yet. So we'll talk about quantum computing in a few weeks. But what matters for now is, yes, we can do matrix multiplication faster than with the Strawson algorithm in practice. And you can take a look at these complexities here. One thing was when we introduced the original complexity, or how to calculate it, of the Strawson algorithm, we say the log2 of 7. The question is, where does this come from? And this is part of the coursework. So in the coursework, you can now finish the coursework about maps and hash tables, which we have just finished. And there's more coursework, like I provide you with the recurrence relation for naive matrix multiplication. So it's your task to derive the worst case running time complexity for this. You can either solve this manually or use the master theorem. And I also provide you with the recurrence relation for the Strawson algorithm. You can solve it and you will eventually get to this solution here. There are some more advanced problems about matrix multiplication. These are only for the super curious students that go beyond what we have done today. Just if you want to learn something else about matrix multiplication and you're all okay with what we have done so far, feel free to do problems 14.3 and 14.4. But those are only really additional ones, and they wouldn't be part of the exam in any way this year. So only up to 14.1 and 14.2. We are skipping the random number generation, and if you're curious to see how to generate random numbers, I taught it 2 years ago. The recording is on YouTube. And another interesting algorithm is how to calculate this one here, which is called the inverse square root, very efficiently. Something we use all the time, for example, to normalize vectors. And if you're wondering how to calculate this efficiently, maybe ask yourself first about how we can actually calculate the square root efficiently. It's again a selected algorithm that is not discussed this year and not relevant to this year's exam. If you're curious, take a look at the slides or the recordings of last year, because it actually shows something very interesting from the game Quake 3 Arena that found a very interesting algorithm how to calculate the fast or the inverse square root very, very efficiently. We discussed this last year, and in 2 weeks, since next week we don't have lecture, we will start looking into prime numbers. I was actually hoping we could already start with prime numbers today, but we needed a little bit more time for the hash tables than expected. So in 2 weeks, we will start looking into prime numbers, and after that, we will be looking into the Plume filter. So I hope you'll have a good weekend, and I'll see you then in 2 weeks, both in the lab on campus as well as for the double lecture as of 2 p.m. Have a good weekend. Take care. Bye-bye.